Greetings. In this video, we'll talk about what the topology is. I'll go over the definition of a topology and yeah, let's get into it. So for the start, we'll talk about it in the context of yet another thing, which might now seem like too many things at once, but the other thing that I'm mentioning is basically topological space. And the topological space is denoted in the way that we have some set X on which we have some topology. So the context of all of this might seem a little overwhelming at once now, but we'll all click together as we go further through it. The point here is that for topology we need some underlying set on which it is defined. And basically the idea is that the topology now for this example, and probably what we're using here, the notation, or explicitly the names for the topology as well as the underlying set of it, are the most generic ones. For topology, the Greek letter tau, and for a set, the capital letter X. So what we're talking about here, if we want to name it, is a topology on set X. And what is a topology? So we have some set X, and let's say we can consider a set can have, for example, 3 elements A, B, C. And a topology is a collection of various subsets of that set, of the set X. So topology, this tau here, will be a collection of different subsets of this set X. Alright? So the topology is a collection of different subsets that belong to, that are made out of the elements inside X. They have to satisfy some conditions, but first of all, let's just look at what subset means. So a subset out of this example set, I'm not saying that this necessarily is X, it can be many different sets, infinite ones, discrete ones, continuous, as well as infinite in the case that, for example, can be discrete, infinitely many, discrete and infinitely many elements, but also continuous infinitely many elements, some part of let's say a real line or something. The underlying set can be many different options, but let's now just consider the idea of a set to make clear what a subset could mean. So a subset of generic set A, B, C, these 3 elements are inside it. Subset is, we can take any element out of it, for example, and that can be a subset. So A is a subset, or the 2 elements A and B together are a subset, or A, B, and C, the entire set is a subset of itself. So these are some examples of a subset. And let's now look at the conditions that a collection of subsets that belong to this set X, so a collection of subsets of this set X, what they have to satisfy in order to be a topology on it. So in order for this tau to be a topology in X, well, it has to be a particular collection of subsets. These subsets have to together satisfy some conditions. The conditions are in general 3, divided into 3 parts. The first condition is that the empty set has to belong to tau. So as the collection of subsets, the empty set has to be there, and also the entire set X itself has to be in tau. So the topology as a collection of subsets of X has to contain the empty set as well as the entire set of which we're doing the subsets. Then second of all, when we take some finite intersection, let's say we have some index I that spans over, let's say, natural numbers or whatever, and let's AI, let's denote that to be a particular one of the subsets, however many, this is just arbitrary, but I'm saying that if we have a finite, or maybe easier way to denote it is for any 2 subsets of X inside T. Alright, so for any 2 subsets A and B, we have that their finite intersection, or their intersection will also belong to tau, to the topology. So the topology as a collection of subsets of X, if we have any finite intersection of those, of any chosen subsets inside the topology collection, the result of that intersection has to also be one of the subsets that is contained in that collection, in that tau, in that topology. So why I'm running it like this is because when we say that A with B intersection is equal to C, then, well, we know that C also has to be inside tau. Therefore, when I talk about finite, then C with D, if D is also in, and C of course is in tau, and D again is another subset, or again in tau, is also in tau, then that also has to be in tau. And it goes like this on and on and on. But yeah, so we're talking about finite number of subsets. They have an intersection, and that intersection must be contained inside tau. We cannot talk about some infinite intersection. There can be situations when we can actually denote an infinite intersection, but that doesn't have to be guaranteed to be inside, because we're talking about finite ones. So this is probably the easiest way to, in general, kind of denote it, that we have finite intersections, and they're close in the way that, again, the subsets, they are also subsets contained in the collection tau. And the third condition for topology is that even infinite unions of the members of the collection of subsets of the members of tau, there will be, so any union of elements, this is probably the easiest to do it with words, any union of elements in tau is also one of the subsets contained in tau. What I mean by this is basically simply that if we have it can be an infinite union even, so if there's infinitely many elements to choose from inside tau, infinitely many subsets of X that are members of tau, then however many we take out of them, random ones, we put them together and take their union, that union also must be a subset of tau, also must be one of the subsets that tau constitutes of, or has inside itself. Therefore, this is the third condition and must be also satisfied. So these are the three conditions for topology. Just to repeat it once again, a topology is on a set X is basically a collection of the subsets of X that together satisfy these rules. That means for many sets X, there can be multiple different topologies. We'll go into something called indiscrete and discrete topologies in another one, but for now we can look at some examples. So, and by the way, why we're talking about this in the context of a topological space is because when you write it like this together is a topological space. So the set, underlying set, along with the topology, that is its subsets collection, that together makes up a topological space, and it's written like this together in this parentheses notation. So let's take an example of a topology. So a topology can be consisting of course, it has to contain the empty set, it has to contain X itself, and then what else can it contain? Well, let's say that X is the set A and B. Well, X itself we can write it as A and B, and then this by itself could be a topology. It's actually called an indiscrete topology, and we'll go into it in another one, because it contains the entire set and the empty set, and only that, and there it would end. But actually, let's take a more interesting example by also adding more subsets. So let's add A as a subset, and now let's verify if this works out as a topology. Well, what we need is to just make sure that the three requirements are satisfied. So 1, 2, 3. Well, the first requirement is there must be empty set, which there is, and the entire set X. Well, that is satisfied. So this one is satisfied. The second condition is any finite intersection must be contained. Well, we have finite intersection between these two, these two, these two. So between these two, well, the intersection is nothing. So this one. Between these two, the intersection is A. So we have it. And between these two, the intersection is nothing, so we have it. So any finite intersection. And then if we take any of these three, or when we took these, different different pairs of these subsets in the collection, put them into intersection, it always gave one of the subsets that are in tau again. So the finite intersection, we could continue and layer it up. We could do 3 different subsets intersections that belong to tau and see that it again belongs to tau. Now this is satisfied, and any infinite union, well, we can add everything that is here. So if we add A and A, B and A together, we have this one. If we add this and this, we have this one. If we add this and this, we have this one. And if we add this and this, we have again this one. So that's also satisfied for any union. If we add everything, well, we have the entire set that's there always. If we add this just to itself with this, when there's just this, and so on. So yeah, indeed, what we need is satisfied, and therefore we can say that this is a particular, this tau is a particular topology if x equals to the elements A and B. So this was an abstract example, but a one that illustrated what a topology can be on a particular defined set, where this one was discrete.